This program is brought to you by Stanford University. Please visit us at stanford.edu.
The last time I told you that proper time is defined by the tau squared is equal to dx squared, the t squared minus the x squared. And the question was, where does the minus sign come from? Well, the whole point of the Lorentz transformations, the whole point of it is that they conserve or preserve quantities like dt squared minus dx squared. They don't preserve quantities like dt squared plus dx squared. If we make a Lorentz transformation to a new set of coordinates, x prime and t prime, then not only is x squared, or let's say t squared minus x squared equal to t prime squared minus x prime squared, but if we take any little differential displacement, dx dt, that it's also true of the differential displacements, that they are also conserved, or that this quantity, the corresponding quantity, dt squared minus dx squared, is invariant under Lorentz transformations. Now, we want the idea of proper time or distance along a trajectory to be Lorentz invariant. We want it to be the same. In fact, that's what we mean by it. We mean something that has physically measurable meaning. Physically measurable meaning means, among other things, that it doesn't depend on the coordinate frame. The quantity dt squared plus dx squared would vary from reference frame to reference frame. If you take the Lorentz transformations and you work out how x and t transform, you'll find out that things like t squared plus x squared or dt squared plus dx squared change when you vary from one frame to another. And so they're not good candidates for invariant, measurable, well-defined, observable quantities. They vary from frame to frame. It's the quantity dt squared minus dx squared which is the invariant. All right, let's start. I see I got something to eat, thank goodness. I was about to faint. Just give me a second to find my place. Good. First announcement. I've been getting a lot of emails from a lot of people, not just in this class, but from all over the place, who watch these lectures and send me a lot of email asking good and interesting questions. The problem for me is that there's too many of them, but on the other hand, very many of them are very, very similar. I try to answer them, and I do answer them for the most part, but I decided there's a more efficient strategy for dealing with this, since so many of the questions are very similar. What I decided to do is to start a blog. The purpose of this blog, incidentally, is not to discuss polemical, political controversy. I have no interest whatever in doing that. I have interest in nothing but answering physics questions, some fraction of which, probably most of them, would come from not this class so much, but from this class in the extended sense of the people who also watch it on the internet. So I decided to try and open a blog, which I managed to do today, just because I got a whole bunch of questions which were similar. And so I'm going to ask you, instead of sending questions to my email directly, send them to the blog. And I'll give you the address of the blog. I never had a blog before. In fact, I never wanted a blog before. But I realized it might serve some purpose, as long as I manage to control myself and keep my polemical side suppressed. which I will do. And so should anybody who is sending mail to me or to the blog. Forget polemics. I won't answer it. Forget whether string theory is not even wrong or just plain wrong, or whether I personally am the trouble with physics or whatever. Forget that stuff. If you have, for example, if you have a question like, why was the sign in such and such an equation on the blackboard plus and not minus? I think you made a mistake. I'll be glad to answer that. I'll also be glad to answer any questions which are real questions which I know the answer to outside the context of this class. And perhaps if I don't know the answer, somebody else does know the answer, so it can serve some good purpose. But as I said, I will not address polemical questions. Anyway, the blog address, for those who want to use it, is, I suppose they're all lowercase, but I have this habit of writing uppercase. Suskind's blog physics, it's all one word, for everyone. Now I can .blogspot.com. No, there was a purpose to making it very long. The purpose is you have to really want the answer. Nobody's going to come to this who isn't looking for an answer to a specific question.
They won't stumble on it by accident.
Yeah.
Or they'll Google it.
Suskind's blog physics for everyone.blogspot.com. And let's use that. I'd rather use that than the usual class. For class purposes, when will there be a class? Will there be a class this Sunday at midnight or whatever? Use the class thing. But if you have a question, a real question about physics, and it doesn't have to be about details of the class. If you have a question about physics, let's post them on this. And that way I don't wind up answering the same question endless numbers of times, which I really don't mind, but it got to be a little bit much. Okay, so now let's get to field theory. Before I go back to relativity, and we will go back to relativity because we're not quite finished with it, but this class is both about relativity and field theory, so I'd like to get started a little bit on discussing what field theory is. Now, we're talking about classical field theory this quarter. I might here and there mention a bit about quantum field theory, just a very little bit, put some of the ideas together with a bit of quantum mechanics. But it's primarily about classical field theory. So what does classical mean? Classical does not mean that it comes from ancient Greece. It means that it doesn't involve quantum mechanics, as you know. So classical field theory is the theory of classical fields. What are fields? Fields are things which fill space and time, electric fields, magnetic fields, gravitational fields. They're conditions in space-time which determine all kinds of things. Yes?
Does classical also exclude relativity?
No. As a rule, the question was, does classical exclude relativity? No. It's almost a technical term. When one speaks about classical, one strictly means excluding quantum mechanics. For example, one speaks about classical general relativity versus quantum versus quantum gravity, classical gravity versus quantum gravity. And so, no, one does not, which way is it? Classical means non-quantum mechanical, and that's all. What does semi-classical mean? I'll tell you when we get to it. It's a good question. But let's talk about what field theory means. Fields mean electric, magnetic, gravitational fields, other fields which also occur in physics. There are a lot of them. not just the usual standard ones that you learn about in elementary physics. There's the Higgs field, there's the Yang-Mills fields, there's the inflaton field, whole bunches of them. And physics makes very clear that those things exist. But what they are is they're fields in space-time that vary from place to place, from time to time, and that need equations to govern how they evolve with time. All right, now field theory, classical field theory is a combination of two basic disciplines. One of them is special relativity. Of course, you can have field theory which is not relativistic. It's perfectly thinkable, but to have a field theory which does not satisfy, fields just mean things which fill space. You can have field theories which don't satisfy the rules of relativity. What I mean by saying you can have them is you can imagine writing down equations for fields which don't satisfy the principles of special relativity. But that's not what this class is about. This class is about relativistic field theory. So it's a combination of the special theory of relativity and classical mechanics. It's classical mechanics applied to the theory of fields. So I want to begin by reviewing the principles of classical mechanics. Was that last quarter? I can't remember. I lose track of the quarters. Fall quarter. What did we do last quarter? Last quarter we did quantum mechanics. Thank you. All right. Let's review a little bit about classical mechanics. One of the ways of summarizing the principles of classical mechanics are through the principle of least action. So let's go back to the principle of least action. We describe a system by a system of coordinates. The coordinates, the typical situation that we're used to, that we're familiar with, is where the coordinates are coordinates describing the location of particles. They don't have to be. They could be any set of coordinates describing a physical system. In particular, they could be the values of fields at different places in space, but we'll come to that. Whatever those coordinates are that describe the state of a system, the configuration of a system, we combine them together and we call them the set of variables Q. Now, in the simple situations that we're familiar with, there typically are several Q's, more than one of them. The Q's could stand for the positions of particles. If there are n particles moving on a line, all the particles moving on the same line, then there are n coordinates, and we might call them x. I don't want to call them x now, and the reason I'm calling them q is because x is going to have some other significance for us. But some number of coordinates q. It could be a single particle moving in 3 dimensions. Then there are 3 q's. In fact, there would be 3 q's, x, y, and z, for a particle moving in 3 dimensions. There would be 3 q's if there were 3 particles all moving in 1 dimension. So the fact that there are 3 q's and not 7 q's or 14 q's or 10 q's doesn't necessarily tell you how many dimensional problem you're working in, but it does tell you how many coordinates it takes to describe a system. So we could label them q sub I, where I runs from 1 to anything. We could even imagine systems of infinitely many particles. We might get a little bit confused then about labeling them, but still, we can imagine systems with infinitely many particles filling all of space from one end of space to the other end of space. But let's stick with, for the moment, with finitely many of them. And the other thing we need to know in order to get started with a system and to predict its future is the velocities, which means the time derivatives, or the rate of change of the q's with respect to time. Q sub I dot, time derivative. So q sub i's are typically functions of time, as are the time derivatives, and the time derivatives are just gotten by differentiating with respect to time. All right, the laws of physics, and as far as we know, all of the laws of physics that we know, all the basic laws of physics, Newton's laws, electromagnetic theory, Einstein's law, Einstein and Newton's laws of gravity, the theory of the Higgs particle, everything that we know about can be derived from the principle of least action. And the principle of least action begins, well, first of all, it begins with a picture. As always, we draw the time axis upward. In the horizontal direction stands, let's put a couple of horizontal directions in, but the horizontal directions really stand for all the possible Q's of a system. So the horizontal directions don't have to be three-dimensional space. They could be 300,000 dimensional space if there were 300,000 particles moving on a line. It simply represents the various coordinates Q1, Q2, Q3, and so forth. And specifying a set of Q's at the beginning, for example, means starting at a point on the space of Q's. All right? So an initial condition corresponds to a set of Q's, which is a point in this space, and a set of Q dots. The set of Q dots tells you the way the point is moving at initial time equals 0, so it gives you some idea of the direction that the various Q's are moving off in. That's the starting point. System described by Q's and Q dots. The principle of least action says that you can determine, not that you can, but the trajectory of all systems. The trajectory means its history. Its history starting with some initial configuration and ending with some final configuration. Incidentally, the word configuration refers to the Q's. It's a technical term. It means the values of a set of Q's. It does not mean a set of Q dots. So when one speaks about a configuration, it means, for example, fixing the location of all the particles without fixing their velocity. So that word configuration, keep in mind. We might ask, given that a system starts at one configuration and ends after a time t at another configuration, exactly how does it move in between? What's the path that it takes through the configuration space? How does it move with time? And the answer is every known system satisfies the principle of least action, which means that there's an expression called the action, which is built up out of the Q dots and the Q's, which is minimized, which achieves the minimum value that it can take on along the trajectory. Physically allowable trajectories are minima of the action. Now, what is the action? The action always has the form of an integral over time, dt, of something that's called a Lagrangian. The Lagrangian is something that's made out of the Q's and the Q dots. So it's some Lagrangian, which depends on Q and Q dot. And one speaks about the action between the initial and final configuration. So that means the integral is from some initial time t1 to some final time t2. And the trajectories that we explore, the trajectories that we're going to explore, the different trajectories that we're going to compare to find the one of least action, are all trajectories which pass through the same 2 points. So we specify a problem by specifying an initial and a final configuration and asking which of the many trajectories will minimize the action. All right, now what is this thing called the Lagrangian? As I said, the Lagrangian is just a function of the coordinates and the velocities, and it typically has, not always, but it typically has a simple form consisting of a kinetic energy T, which depends on the Q dots, and I'll write down an example in a moment, minus a potential energy. The potential energy only depends on the Q's. It does not depend on the Q dots at all. It depends on position, but not velocity. the kinetic energy sometimes depends on both. The simplest systems that we can think about, particles moving and so forth, the kinetic energy as a rule depends only on the velocities. And so, for example, if Q actually represented, if the Q's represented points moving on a line, let's imagine points moving on a line, a whole bunch of them. Some are moving this way, some are moving that way, and so forth. Then the Q's would simply stand for the positions of the points along the line. Their velocities would be the Q dots, and their kinetic energy would be 1/2 the mass of the ith particle times the square of its velocity. So we would write that T is equal to 1/2 a sum over all the particles, sum over I, particles labeled according to I, 1/2 the mass of the ith particle times Q sub I dot squared. And then we would have minus the potential energy, minus U of Q. And this U of Q would in general depend on all of the positions of the particles. It would not itself be a sum over individual particles in general. For example, there might be forces between pairs of particles. In that case, the U's might come from a sum over pairs of particles, but in general, it's just a potential energy which depends on the positions of all the particles. This is a simple example coming from the mechanics of particles. More generally, T could, I'm sorry, I've written something silly here. T minus U is equal to this. T minus U, okay? Keep in mind one thing, the Lagrangian is not the energy. The energy is the kinetic energy plus the potential energy. Okay, so that's the basic structure of classical mechanics. Pick a pair of points, one we can think of as an initial and the other a final starting point and ending point. 2 points in the configuration space, separated by a total amount of time, call it t. Compute the action, the integral of the Lagrangian from the beginning of the trajectory to the end of the trajectory. Clearly depends on the trajectory because the Q's and the Q dots depend on the trajectory. And then explore around and look for the trajectory which minimizes the action. That will be the solution to your problem. Okay. That's the principle of least action. Without it, we would have no concept of energy, momentum, and so forth. And I refer you back to the previous to the previous lecture series on classical mechanics for the details. But there's one detail which is important. The detail which is important is one might get the feeling from this that there's something teleological about physics. Teleological, what is the word teleological? Can somebody define teleological for me? I know what it means, but I can't define it.
Pointed toward a goal.
Pointed toward a goal, or somehow mysteriously knows about the end point as well as the beginning. There's something about this which seems a little bit too teleological. Whereas we know that the properties of physical trajectories are things which can be determined from local differential equations, that the behavior of a trajectory can also be described not by this global, I call it global because it involves a whole trajectory, not by global constraints like the principle of least action, but there's Newton's equations, F equals ma, which tells you what the trajectory does at each little increment along the trajectory. And so there's some other description which is local along the trajectory. Differential equations, that means. What's the connection between the two of them? Well, the connection is actually very simple. Supposing I take a trajectory which I am suspecting is the solution of my problem. And now supposing I vary it a little bit, just vary it a little bit along the trajectory, then I will necessarily increase the action. So if I knew that the action was minimum for every little displacement that I could make of the trajectory, that would be the same as knowing that the action was minimum for the whole trajectory. So if I know the trajectory gets to here, and I know it gets to here, then I can ask a perfectly local question, or at least a small question. Let's call it a small question instead of a big question. I can require that the trajectory has the least action between these 2 points. And that's a condition which really only depends on what's going on in the neighborhood of those 2 nearby points. If we bring those points very close together, the condition for minimizing the action over that small region there becomes a differential equation. It becomes the Euler-Lagrange equations of motion, which I won't derive, but that's exactly where they come from requiring that the action be minimized with respect to a small little deviation of the trajectory. And those equations are differential equations. I'll write them down. We've studied them before, but we're just reviewing now. The Euler-Lagrange equations are simply for each, there's a separate equation for each one of the coordinates q sub I. So if there are 100,000 coordinates, then there are 100,000 equations, as there should be, because there should be a separate equation for each coordinate. If we're going to determine all of the coordinates and the way they move, there had better be a lot of equations. Basically, F equals ma for each particle in the system, or for each component of motion of each particle. The equation for the ith coordinate is you first construct the derivative of the Lagrangian with respect to the velocity associated with that coordinate. The derivative of the Lagrangian with respect to q sub I dot. All right, so let's see. Let's read this off. That would be, in this case, partial of L with respect to qi dot. I here could stand for 7 or 14 or 23 or however we label the particles. Pick one. Partial of L with respect to q sub I dot, that's just equal to m q sub I dot. This quantity is also known as the canonical momentum conjugate to the coordinate q, and it's often written p sub I. The canonical momentum, and notice that it is the momentum, mass times velocity, for the usual particle on a line. P sub I is m sub I q sub I. That's this. We differentiate that with respect to time along the trajectory. Along the trajectory, we differentiate that with respect to time minus the derivative of the Lagrangian with respect to q sub I. And that's equal to 0. For each one of the coordinates, these are the Euler-Lagrange equations, and they're equivalent to Newton's equations. Newton's equations, one for each particle. Let's check that. Let's see, let's work that out. The derivative of the Lagrangian with respect to q sub I, that's m q sub I dot. We have to differentiate that once more. So this term here becomes m. We always assume that the masses of particles are constant. They don't vary. So that's m times q sub I double dot. An extra derivative here. It's this. And that's, of course, mass. M sub I, thank you. M sub I, q sub I double dot. What is that? That's mass times acceleration of the ith particle, for example, as an example. And that is equal to, let's put this on the right-hand side, dl by dq sub I. All right, now, where are the q sub i's? In this expression, for the simple Lagrangian here, which has the form of a function of velocities plus a function of positions, typical situation, the only places that the q's themselves appear is in the potential energy. So this gives us then minus the derivative of potential energy with respect to q sub I. This, of course, is just the force on the ith particle. The gradient of the potential energy with respect to position, or minus it to be more precise, is the force on the ith particle. For our purposes, we'll just define this to be the force. Notice it depends on position, it does not depend on velocity. Now, there are velocity-dependent forces in nature, and we'll come to them. They tend to happen when there's mixed q and q dot dependence in the Lagrangian here. There are velocity. Anybody know any examples of some velocity-dependent forces? Yeah, the magnetic force on a not on a magnet, but on a charged particle, on an electrically charged particle. The faster it moves, the larger the force on it. So this is not the most general form of Lagrangian that you can write down, but this rule, principle of least action, is the most general form that we know of the laws of physics. Okay, so there we are, F equals ma, F on the right-hand side, ma on the left-hand side, and that's a typical example. What is field theory? Field theory is a theory in which the degrees of freedom are fields which fill space. They also vary with time, but for the moment let's concentrate on the way they fill space. The Q's are the values of fields at different positions in space. The reason I didn't want to call the coordinates of a particle x is I wanted to reserve x for another just for position, abstract position, not necessarily the position of a particle, not necessarily the coordinate that will go in the Lagrangian, but just a position in space. That position in space might not be the position of a particle, it might just be a position in space. In a field theory, a position of space labels the location of a degree of freedom. It is not itself a degree of freedom, but it labels a degree of freedom. So, for example, you know what I think I'll do? I think what I will do is work out an example of a field theory from the beginning, showing you how it comes about from a simple mechanical system, which when you take a certain limit becomes a field theory. I think it will do more to explain the idea than to describe it abstractly. The system is a collection of springs connected together to form a string. Not a string of superstring theory, but a violin string, or something like a violin string. A slinky is even a better example. But here's the system that I want to begin with. It is, in fact, a violin string or a guitar string. A string connecting 2 points. What do you call a thing that holds the string, the ends of the string? A post in a violin? I forget. One end is a bridge. The other end is the thing you turn. The hook? Oui? Egg? Peg. Peg. Ah, okay. Yeah. So from the bridge to the peg, but we don't have to distinguish which end is the bridge and which end is the peg. We have a string stretched out. Whoops, I missed the peg. There it is. All right. Now I'm going to make a simplifying assumption about the string. The points of the string don't move horizontally, they move only vertically. That's a simplifying assumption, but it's a pretty good assumption. It's much easier, if you think about it for a minute, it's much easier to get the string vibrating vertically than it is to get it vibrating horizontally. It typically the string is much stiffer to get it moving horizontally than it is vertically. So let's ignore the horizontal motions of the points of the string and only concentrate on the vertical motion. Now, to get a handle on it, let's begin by imagining that instead of a string, we have a collection of springs. And a collection of springs means a collection of mass points which move vertically but have springs. I'll draw the springs in a different color. Have springs connecting them. In the limit that we take a continuously infinite collection of mass points, in the limit that we take that continuous limit, this string becomes a field, or a mathematical model for a field. It's not a field in real space, but it has the mathematical structure of a field in a space that exists between the post and the peg and the other end, whatever it's called. Okay. In other words, we can define a variable. It's really just the height of the mass point. Incidentally, there's nothing to prevent mass points from going lower here also. We could call it y, but I'm not going to call it y. I'm going to call the height of the ith point, I'm going to label it phi sub I. Phi sub I is simply the displacement in the vertical direction of the ith mass point. And I want to study the equations for this thing. We can get a pretty good idea. We know what's going to happen. Waves are going to go up and down. When we take the limit, it's going to form a mathematical string. The string is going to have waves that can propagate up and down. There'll be waves of different frequency, different wavelength, and so forth. We have a pretty good idea what's going to happen. But we want to describe this using the laws of mechanics and using in particular the principle of least action. Or more specifically, the Euler-Lagrange equations which follow from the principle of least action. All right, so let's see if we can write down an action for this, literally thinking of it as a collection of mass points and springs. Now, let's assume that the separation, let's call the horizontal axis the x-axis. Notice that x labels a point, but it is not itself a coordinate of the system. The phi's are the coordinates. The things which are the q's are the phi's. They represent the dynamical degrees of freedom. They represent what you need to know in order to get started. The x's, the x just labels which one you're talking about. This is x equals whatever. This is x equals twice whatever, 3 times whatever. And let's assume that the distance between neighboring points along the x-axis, let's call that epsilon. At the end of the day, we're going to add more and more and more mass points and shrink epsilon to 0 in such a way that they continue to stretch between x equals 0 and x equals whatever the end point is here. So as we add more and more mass points, we'll shrink the gap. Now, first question. What should we take to be the mass of the ith point? Supposing we took the mass to be a gram or a kilogram or whatever. As we add more and more mass points and fill up the gaps with more and more mass points, it's pretty clear that the mass of that string is going to become infinite as we add more and more mass points if the mass per particle is fixed. What we're going to want to do is imagine that a segment of string has an overall mass which doesn't change as you add more and more points. To do that, we're going to have to shrink the mass of the mass points as we add more particles. In particular, we'll have to assume that the mass of the ith particle is proportional to epsilon. Let's just call it epsilon. The distance. As epsilon shrinks smaller and smaller, and we crowd more and more mass points in there, we'll shrink the masses so that the net mass between 2 points on the x-axis here stays fixed. So that means the mass of the ith point is proportional to epsilon as it shrinks. And let's just take it, all the mass points to be the same, mass of size epsilon. And let's write down the kinetic energy. Now, the kinetic energy is the energy of motion along the phi axis, which means the vertical axis here. What is it? The kinetic energy is 1/2 the mass of the ith particle. Well, first of all, we're going to have to sum. We'll eventually summation over all the particles, the mass of the ith particle, which is epsilon, and then the square of the velocity, which is, after all, just phi dot squared, phi sub I dot squared, divided by 2. 1/2 mass times the velocity squared. That epsilon is in a rather convenient place for later purposes. Let me tell you what the later purposes are. Later on, we're going to replace this sum by an integral. When we start filling this up with more and more dense points, this sum is going to turn into an integral. That's obvious. Let me just remind you of the relation between sums and integrals. If we have a function on an axis, and the interval between neighboring points is, well, whatever that interval is, let's call it delta x, then the definition of an integral, f dx, is just a summation over all the values of the functions at all these discrete points, summation over I, of the value of the function at the ith point, call it x sub I, times delta x. That's what this dx is there. That dx really means delta x. And, of course, f of x times delta of x is just the area under that. Height f with delta.
I have a question.
Yeah.
When you say that x labels the points,
Yeah.
would that be something like x equals x0 plus I epsilon? In other words,
I know what you're asking. I know what you're asking. The x's, of course, up at this point are discrete. All right? There's not a particle at every x. There's a particle at a discrete collection of x's. The allowable x's that correspond to particles are separated by an interval epsilon. I think that's roughly what you're asking.
Well, I is already an index, and x is...
Yeah, there's a redundant, that's right, there's a redundancy of notations here. I could choose to label the particle by I, or I could choose to label it by x sub I. The reason I have the redundancy is to reinforce in your mind, first of all, that we're just talking about different particles. That's the I index. But later on, we're going to take a limit where the identity, the discrete identity of the particle is going to be replaced by a continuous identity of degrees of freedom labeled by x. It will no longer be a good idea to label them by I, we'll label them by x. But x, at this point, x and x sub I are sort of redundant descriptions of the name of the particle, all right, the label for the particle. Good. All right, now the connection, though, between integrals and sums is, of course, integral f of x is the limit. I've suppressed the limit, but you know, of course, that there's a limit in which delta of x goes to 0, in which delta of x goes to 0. Delta x in this example is just epsilon. So an integral is a sum multiplied by epsilon. Well, here we have a sum multiplied by epsilon. It's not too hard. I'm not going to use this yet, but I just want to point out what this epsilon is doing here. It's quite obvious that this is eventually going to be replaced by the integral dx of 1/2 phi dot squared. The epsilon will become the dx. That's what happens to epsilon. Phi dot squared, well, phi will, instead of being a function of a discrete index, will become a function of x, and the sum will become an integral. So it's good to have this epsilon there. It's in just the right place to replace this infinite sum by an ordinary integral. I'm not going to use that yet. We're going to come back to that. Now, what about the potential energy? The potential energy of a spring is proportional to the square of the displacement of the spring from its equilibrium position. All right. Now, each one of these springs, just think of it that the equilibrium position of the springs only respond to vertical motion. Let's pretend the springs only respond to vertical motion. And they tend to pull neighboring particles together. There's no direct interaction between particle number 13 over here and 156 over here. The only interaction is through the intervening particles. The direct interaction is between the neighboring particles. When you separate the neighboring particles vertically, the spring gets stretched. The stretching of the spring is proportional to the difference phi I, let's say phi I plus 1 minus phi I. That's how much the spring between I and I plus 1 is stretched. So for example, this might be the ith particle. This might be the I plus first. I plus 1 could be 7, I could be 6. All right. This is how much the spring connecting I and I plus 1 is stretched. If I and I plus 1 are at the same height, that spring is not stretched. It's when they're pulled apart that it's stretched. So that's how much it's stretched. And the potential energy of a stretched spring is proportional to the square of the distance that it's stretched. So that means we should expect the potential energy in that spring to be proportional to the difference of the two coordinates squared. We need a coefficient, a spring constant in front of it. The usual formula is to put a spring constant divided by 2. That would be the potential energy of a single spring. We're going to take, and you'll see why. Incidentally, all right, let me explain why. Supposing you have a spring. It's made of iron or whatever a good spring is made out of. It could be a rubber band, anything that forms like a spring. And it has a certain spring constant, K. It represents the stiffness of the spring. All right? It's Hooke's law, spring constant K. Supposing you cut the spring in half this way so that it's only half a spring and throw the other half away. What happens to the spring constant of the half spring? Is it bigger than or less than the spring constant of the original spring? I hear every possible answer, and then some. It's bigger. The spring, it's stiffer. If you cut a spring in half, it's stiffer. It's harder to stretch it a centimeter. A tiny, tiny spring is much harder to stretch a centimeter than a long spring. So the spring constant, if we took this spring and replaced it by 2 springs, each one of those springs would have twice the spring constant. That means the spring constant has the epsilon in the denominator. The smaller epsilon, the bigger the spring constant. All right, with that, and we'll see that that works out just right to convert differences to derivatives, integrals, summations to integrals. But that's the physical reason why the smaller the spring is, the larger the spring constant, which means we ought to put the epsilon in the denominator, not in the numerator. Okay, let's do that. Let's put an epsilon in the denominator, And then there's a possible coefficient, a possible numerical number that goes in the numerator. It might distinguish different kinds of materials. It might distinguish how tightly the string is stretched. Just some numerical coefficient there that actually carries some dimensions with it. And I'm going to give it a name. I'm going to call it c squared. I call it c squared for reasons that will become clear. Okay. This is the potential energy of a single spring. But now we should add them all up, all the pairs, all the neighboring pairs, add them all up to find the total potential energy. All right? So the potential energy is the sum over neighboring pairs of phi I plus 1 minus phi I squared, c squared, divided by 2. Let's make some room here. U is equal to c squared over 2 epsilon times the difference of phi at neighboring points squared, summed over all the neighboring pairs. Well, now we have everything we need to write down the equations of motion of this system. We have t, we have u, we can write down the Lagrangian. And once we have the Lagrangian, we can apply the Euler-Lagrange equations to each one of the separate phi coordinates. Okay, so the Lagrangian then is the summation over I, epsilon over 2. I can take the epsilon over 2 on the outside. Let's take it outside. Epsilon over 2, summation over I, phi sub I dot squared, and then another term minus u. Remember, you subtract the potential energy, minus summation, well, let's minus c squared over 2 epsilon, summation. Now, you know what I'm going to call this? I'm just going to call it delta phi squared. Delta phi means the difference between phi on 2 neighboring sites. Delta phi squared. But it does mean phi I minus phi I plus 1 squared. It's, yeah, it's delta phi I squared. Yeah. I'm not sure. The only reason I didn't write it is because should we call it delta phi I or delta phi I plus 1? But you know what I mean. It's just saving me, it means this. It means this, and you sum up all the contributions. Okay, let's now take that. Before we take the limit, let's work out the equations of motion, and then take the limit in which the number of springs becomes continuously infinite. All right, let's put this up on the top.
Where did we get the sign?
Well, the potential energy is clearly positive because it corresponds to a Hooke's law where you have to do work to stretch the spring. So the potential energy is positive. You could imagine a system with the opposite behavior, but it would have very bad properties. It would be unstable. But it's a good question. Let me come back to it when we have when it doesn't interrupt the flow of the thought. Yeah, the question was, where do we get the sign of this from? We get the sign from t minus u. But why? But that simply replaces it with the question, why is the potential energy positive? The potential energy is positive because you have to do work to stretch the spring. Okay? That, of course, is an assumption about springs. You can imagine crazy springs where when you pull them apart, they tend to push you even more apart. And it's actually the condition that the spring has a restoring force instead of an anti-restoring force. Good. Okay, so now let's work out our Lagrange equations of motion. Let's go to the ith. Whenever I do this, I get completely confused by all these indices. The indices drive me crazy. And what I have to do is I have to work it out for I equals 7. Once I've worked it out for I equals 7, I see the pattern and I can work it out for any I. So let's focus. It doesn't have to be 7, but let's focus on I equals 7. We're going to work out the equation of motion for phi sub 7, or phi of x sub 7, phi sub 7. All right. Where does phi 7 occur, and where does phi dot 7 occur? Phi dot 7 occurs in only one term here. So the derivative, partial of L, with respect to phi dot 7 is just equal to epsilon times phi dot 7, right? Did I get it right? Yeah. Okay, now once I do that, then I look at it and I say, I got the pattern now. Phi I dot is epsilon phi sub I. Actually, by now I've done this enough times that I don't really have to plug in 7. But when it comes to this term over here, this one is confusing enough that I have to focus. Think 7, think 7. All right, so let's now calculate, let's now differentiate it, d by dt. That's this. All right, so that's the left-hand side, or the first term in the Euler-Lagrange equation for phi sub I. All right, now let's focus on the potential term. We have to compute, for the right-hand side, minus du by t. We have to compute the right-hand side. That's equal to minus du by d phi 7. Phi 7 enters into 2 of these, and only 2. Only 2 terms here contain phi 7. The one that involves a spring between 6 and 7, and the one that involves a spring between 7 and 8. None of the other springs involve phi 7. So there's going to be 2 terms. All right, let's just work out what they are, the 2 terms involving phi 7. So u, that particular term, is c squared over twice epsilon phi 8 minus phi 7 squared, which incidentally is the same as phi 7 minus phi 8 squared. Okay, doesn't matter which order we write it. Phi 7 minus phi 8 squared is the same as phi 8 minus phi 7 squared. And then plus c squared over 2 epsilon phi 6 minus phi 7 squared. And again, it doesn't matter whether we write phi 7 minus phi 6 or phi 6 minus 7. They're the same thing, squared. Okay, now we have to write here du by d phi 7. Du by d phi 7, first of all, contains c squared, the minus sign from the defining minus sign over here. And now c squared over 2 epsilon times the derivative of this thing here with respect to phi 7. What's the derivative of this with respect to phi 7? Well, it's twice phi 7 minus phi 8. Is that right? Yeah. Say it again? Phi 8 minus phi 7, yeah. Well, wait a minute. It doesn't matter whether we write phi 7 minus phi, let's see. I think it's phi 7 minus phi 8. Yeah. Phi 7 minus phi 8, right. So it's phi 7 minus phi 8. No 2. The 2 from down here cancel the 2 when I differentiated. Oh, I have it there. I should have erased it. Good. Thank you. Now there's the term which is entirely identical, except instead of 8, we have 6. No difference other than the substitution of 6 versus 8. And so there's another term which is plus phi 7 minus phi 6. Let's see if we can see what the pattern is. Let me write the general pattern. The general pattern now is epsilon phi I double dot is equal, it looks like minus, I think I got the minus right, c squared over epsilon, c squared over epsilon, twice phi I, well, let's write phi I minus phi I plus 1 plus phi I minus phi I minus 1. So basically what's happening is the 7th spring is being pulled by both the 8th and the 6th spring. Okay? And each one of these appears there. Now, let me write this in a slightly different form. Let me write this as phi, well, let's write it as, let's change the sign here. Let's change the overall sign. Put a minus here, a plus here, a minus here, and a plus here. Okay? All I did was take the minus sign and bring it on the inside of the parentheses here. Now, here we have phi 8 minus phi 7. What do you think is going to happen to this phi 8 minus phi 7 when we try to take a limit in which it becomes continuous? What happens to the differences when you shrink the gap between things? Well, indeed they go to 0, but before they go to 0, just before they go to 0, they're proportional to the derivative of phi. Right? Differences become derivatives. All right, we'll keep that in mind. In particular, notice there's an epsilon in the denominator there. So it looks like we're going to get some kind of derivative. Now, then there's minus, and let me put in parentheses minus phi 7 minus phi 6. So I have phi 8 minus phi 7 minus phi 7 minus phi 6. Any idea what this whole thing will become? The second derivative. It's the difference of the differences. The difference between 8 and 7 less 7 and 6. This is going to become a second derivative. All right, but before we do that, let's divide by this epsilon here. And then, well, let's not divide. Let's just write down the equation of motion. Epsilon phi sub I double dot. I'm now letting 7 be I, is equal to c squared over epsilon times phi I plus 1 minus phi I, that's this one, minus phi I minus phi I minus 1. Now this is an awkward looking thing, but when we fiddle around with it, we'll see that this is a very simple wave equation. Very simple wave equation. Let's divide by epsilon on both sides first. Then we get epsilon squared downstairs. All right, now let's take one of these epsilons and group it right here. I've used up one of the epsilons here by bringing it inside the bracket. What is this going to be? This, in the limit in which epsilon goes to 0, is going to be the derivative of phi with respect to x, but evaluated at a point midway between I and I plus 1. We can think of it that way. It's sort of symmetric between I and I plus 1. You can think of it as the derivative of phi with respect to x, evaluated halfway between I and I plus 1. What about this one here? That's minus the derivative, minus the derivative of phi with respect to x, but not at the same point, at a point which is shifted one less. All right, so if this is halfway between 7 and 8, or halfway between 8 and 7, then this one is halfway between 7 and 6. So this is the difference of derivatives. It's the difference of derivatives evaluated at 2 points separated by distance epsilon. You can think of it as the difference of d phi dx when you move a step epsilon. But what happens when I divide that by 1 over epsilon? What happens to it? What's it become? The second derivative. This just becomes, in the limit that epsilon goes to 0, becomes the second derivative of phi with respect to epsilon squared. Now, notice that none of this would have worked out very nicely had I not put the epsilons in the right place to begin with. For example, had I made the mistake of thinking that the spring constant, x squared, thank you, second partial of phi with respect to x squared. Had I put the epsilons in the wrong places, they would have showed up in the final equation in some form which would not have allowed me to take a limit. So here we are. Here's the final equation. Phi, oh, what happened to c squared? We left out c squared. C squared. Phi double dot, or let's write it, second partial of phi with respect to time squared is equal to c squared times second partial of phi with respect to x squared. Or even better, well, I don't know, better or different, let's write it this way. I like to write things which are equal to 0. Second derivative of phi with respect to time minus c squared times the second derivative of phi with respect to x squared is equal to 0. All right. Now, that's a nice equation now because epsilon has disappeared out of it. Of course, epsilon is still there, but the point is we've made some approximations where we approximated discrete differences by derivatives. Those approximations become good approximations, become exact in the limit that epsilon goes to 0. So we don't even really have to do anything to get the limit in which epsilon goes to 0. Epsilon doesn't even appear in the equation anymore. Now, as I said, I emphasize, it doesn't appear in the equations because we made some approximations that epsilon was very small. The real point is that the limit epsilon goes to 0 is a nice, smooth limit where epsilon drops out of the equations. And the equation for phi just becomes a simple wave equation for waves which propagate up and down the x-axis. With what velocity? C. Did I get it wrong? Wait, hold on. Let's just check the dimensions of C. I've done this more than once wrong. Let's check dimensions. Okay, so apart from the dimension of phi, which I don't care about since it appears in both of these, here I have a dimension 1 over time squared, much equal a thing with dimension c squared over x squared. All right, so it appears then that whatever c is, it has dimensions of x over t. I think that's velocity, isn't it? I think I got it right. Yeah, you did. I did. Yeah. So c is the velocity of propagation of the waves up and down this string. Excuse me a second. Hello, hello. Hello. We have a class and we can get the, it's okay. Shh, shh. Thank you. That actually, in this case, for this simple wave equation, it's the only speed. All right. Now, of course, yes?
Can you give an example with the springs where it's least action but not minimum energy?
Sorry,
Those are different. You said least action is different than minimizing total energy.
Wait. Yeah. Minimizing the energy is a thing you do to find the equilibrium configuration. Okay? So for example, if we just had a single particle, a single spring, just a, then it would be q dot squared over 2m. The energy would be plus, the Lagrangian minus, plus or minus, depending on what we're talking about, Lagrangian or energy, some spring constant over 2 times q squared. Now, minimizing the energy, in this case, would correspond to q dot equals 0 and q equals 0. Right? That would minimize the energy. That corresponds to the equilibrium configuration of the spring, the static, unmoving equilibrium configuration. The principle of least action has to do not only with equilibrium, but has to do with any kind of motion of the system, oscillations back and forth, whatever it does. And the least action is determined in terms of the minus sign, least energy in terms of the plus sign. We can come back to this distinction between Lagrangians and energy. I didn't want to do that now. I wanted to show you rather how one goes from a mechanical system to a field theory. Yeah.
Can I go back, way back? When you decided how much the stretchiness was, why did it only involve the vertical and not the horizontal distance?
Okay. Yeah, let's go back over that a little bit. Now, first of all, let's assume, this is an assumption. It's an assumption that can be justified, but I don't want to justify it now. Let's assume that the springs, that the mass points only move vertically, that they don't have any horizontal motion. Right? Somewhat arbitrary assumption. I will tell you that it's much harder to get them moving this way, but let's assume it for the moment. All right, now, the energy in a spring is typically proportional to the square of the separation between the two mass points. And in this case, of course, the separation has two components. It has a vertical and a horizontal component. I presume that's what you were asking about. Yeah, okay. So let's look at it. The horizontal displacement is epsilon, and the vertical displacement is phi. What is the distance between this point and this point? Well, it's the square root of phi squared plus epsilon squared, right? But the energy in the spring is not proportional to the distance, but the square of the distance. The square of the distance is just phi squared plus epsilon squared. Right? So the energy in the spring is phi squared plus epsilon squared. But epsilon is just a number. Each one of the springs is stretched by amount. It's just a number. It's fixed. It doesn't depend on phi. So when I add up all the potential energies, there are all these contributions which are the epsilon squares, but they're just a single overall number.
Don't they blow up too fast?
They do blow up too fast, but they're still just a number. And number added into the energy doesn't affect the equations of motion. The only dependence of u on phi is this term here. Okay? So we don't have to worry about the other term just because it's a constant and can't affect the motion of the system. That's the reason for writing it in this form as just phi squared. If the energy was the magnitude of the distance, then we'd have to be a little bit cleverer. But in this case, it's the square of the distance, and the square of the distance just has the two terms additively. And when I add them all up, I get a whole bunch of epsilon squares, but they don't do anything. So for all practical purposes, then it's just phi squared. All right, this is, if you like, it's the derivation of a field theory from a discrete system in the limit that the discrete system gets more and more dense. Let me just very quickly mention the real point here was deriving the equations of motion from an action principle. Let's write out the action. Let me show you that the action can be written as an integral. And let's see what the action is. When I say it can be written as an integral, I mean in the limit that epsilon is small. I'll tell you what, let's take a 5-minute break before I do that and come back and then write the action in a neat form. Needless to say, I did not mean to imply that this variable c is the speed of light. But notice that in this way we did derive an equation that says unambiguously that the speed of motion along this string is c. Now, does that mean that special relativity is satisfied for this string? Not really. By special relativity, I mean that every observer would see the string, the sound waves or the waves in this string moving with the same velocity. They wouldn't. If you were moving past the string and the string was standing still, you would see the waves moving in one direction faster than moving in the other direction. And that's because we're really not talking about special relativity here. We're just talking about a collection of ordinary non-relativistic particles connected by springs. And there was no expectation that, that everybody would see sound, or not sound, but waves vibrating up and down the string with the same velocity. So, well, we'll come back to that. However, this is a model for how wave propagation and field theory occurs and it derives out of classical mechanics. Anyway, let's come to the action and write the action in a form.
Where was the mass in
Where was the what?
Is there something like mass in any of this?
Is there something like math or mass? Mass. Like kilograms. Yeah, there was. It was this epsilon here. Now I could have put, all right, let's go back. Let's not call this c squared for the moment, okay? Let's just call it kappa. But it's not the ordinary spring constant. The ordinary spring constant is kappa over epsilon, all right? And let's call this epsilon times mu. Mu for mass, but mu is not the mass. Epsilon times mu is the mass. Okay? Then we would have gotten the equation epsilon, we would have gotten the equation mu phi double dot coming from this term is equal to kappa, I think, times second derivative of phi with respect to x squared. the epsilons would still cancel. The epsilons were in places that has them disappear out of the final answer.
Potential doesn't have the mass, but the kinetic term does.
Yeah. Kinetic term has the mass, potential term has a spring constant like factor. All right, so then I would just divide this by mu, and I would say that the velocity of propagation, c squared, the square of the velocity, was kappa over mu. So I could have left a parameter mu here, and I could have left the parameter kappa there. Now, in the way that I worked it out, I set mu equal to 1, and I called kappa c squared. All right, good. Incidentally, you could always choose to set mu equal to 1 here. You could absorb it into the definition of phi. You could rescale phi so as to eat up the factor mu here. When you did so, you wouldn't be able to eat up. You wouldn't be able to eat it up out of this term also. So you have your choice. There's various ways you can do this. Let's talk about the Lagrangian and the action of the system. In particular, I want to go to the limit epsilon goes to 0, in which the mechanical system becomes a field theory. Here's the Lagrangian. Let's get rid of the mu here and replace kappa by c squared as we had it originally. Okay. Now, this sum, epsilon, let's remember the connection between integrals and sums. An integral dx of anything, let's say f of x, in the limit is equivalent to, let's just put a double arrow there, is the same thing as the sum of f of x over the discrete set of points, x sub I, let's say, and the dx becomes epsilon. The dx becomes delta x, and in our case, delta x is epsilon. So that's all we have to do is, to replace sums by integrals, and likewise to replace derivatives or differences by derivatives, not necessarily the same function, but a function df by dx is, of course, a replacement in the limit for f of x plus epsilon minus f of x divided by epsilon. All right, we use that. We use that when we replace these things here by derivatives. Okay, let's go to the action and see if we can work it out and find that it's a nice integral of things that make sense from calculus point of view. The first term in the action, that's easy. Epsilon times the sum of phi dot squared. According to this rule, it should just be replaced by the integral dx. 1/2, that 1/2 is the 1/2 that appears out here. The epsilon goes away because it's really just dx times phi dot squared. That was easy and painless. Let me write it phi dot squared times dx. Integrated from where to where? Well, integrated from the bridge to the peg, so to speak. Integrated over the range of x. Let's call it from the bridge to the peg. This is the Lagrangian, but so far this is just the kinetic term in the Lagrangian. Okay? This is the kinetic term in the Lagrangian. Now for the potential term in the Lagrangian. So let's okay, the potential term in the Lagrangian, that's u, or we want minus u, but let me write down u. That's equal to summation c squared, well, let's take the c squared outside, over 2, delta phi I, that means phi of I plus 1 minus phi of I squared divided by epsilon. All right, now I don't have enough epsilons downstairs here to make it the derivative of phi with respect to x squared. This looks like it wants to be the square of the derivative of phi, but it doesn't have enough epsilons downstairs. On the other hand, it also doesn't have enough epsilons upstairs to turn it into an integral. You need an epsilon upstairs to turn it into an integral, but you need another epsilon downstairs to turn this into a square of a derivative. Well, that's easy. Just put an epsilon in there in the numerator and another epsilon downstairs in the denominator. Now we have something which obviously can be turned into an integral. I want to subtract the potential energy. So that's minus 1/2. The 1/2 is the same 1/2. C squared over 2 minus c squared over 2. Epsilon in the numerator just becomes dx again. Let's put integral dx. That's the epsilon in the numerator. And then each one of these becomes each factor here becomes a derivative of phi with respect to x. Squared. No more epsilon. Epsilon is gone. It smoothly disappeared into the definition of derivatives and integrals. Okay. So now I can write down the action. I've written it, but or I can write down the Lagrangian. The Lagrangian L is 1/2 the integral of d phi by dt squared. That's the first term. That's the same as phi dot, d phi by dt squared, minus c squared d phi by dx squared. And that's it, dx, all times dx. That's the Lagrangian. Now notice the Lagrangian is an integral now. It's not a sum over terms. It's become an integral. If we draw space-time, let's draw space-time. Time, space, x, and in our problem, x only varies between the two ends of the string. So what do we call this again? I keep forgetting the names of the parts of the violin. The bridge and the bridge end and the peg end, right? All right, so space-time is all between the bridge and the peg. Of course, there will be nothing to prevent us from imagining an infinite string, but let's have a more realistic violin for the moment. From the bridge to the peg is where space-time is, and time can go from minus infinity to infinity. All right. The phi's are labeled by the points along the x-axis, and the Lagrangian has morphed from a sum over points and springs to an integral over x. All right, that's the Lagrangian. But what about the action? The action is the integral of the Lagrangian with respect to time from some initial to some final time. So let's pick an initial time over here, t initial, t final. Before we write it, let's remember what we're supposed to do. We pick an initial condition, and an initial condition means we specify the q's. Well, what are the q's in our problem? The phi's. Instead of having a discrete collection of phi, we have a phi at every point along the horizontal axis. So we set up the problem of saying, supposing phi takes on some particular functional value, some particular function initially, phi of x initially, let's call it phi initial here, and phi final here. What is the history of the field theory? What is the history of the motion of the spring which interpolates between them? Right. What's the action? The action is just this Lagrangian integrated over time. So let's just write it. Action Notice how symmetrical it's become between space and time. It has derivatives of phi with respect to time squared. Now, of course, in the setting that we're going to be interested in, c is going to be equal to the speed of light. And as everybody knows, the speed of light is 1. So let's just work in units in which the speed of sound, light, violence, propagation, whatever it is equal to 1. That's just a choice of the relation between time units and space units. Here we wouldn't be using light years and years. We'd be using how far does a signal travel along a violin string in 1 second, and that sort of thing. But if we chose units in which the speed of propagation was 1, then we would have a marvelously simple expression for the Lagrangian involving phi, second derivative of phi with respect to t, and second derivative of phi with respect to x, integrated over x and t. In other words, integrated over this whole space-time region. I note for you the existence of this minus sign. Right now, I think we're close to finishing for the evening. I'm getting tired, but I think it should be apparent to you that this minus sign that's there has something or other to do with special relativity. It's somehow connected to the x squares minus t squares, which represent invariant quantities. Yeah?
I'm getting confused between second derivatives.
This is not second derivative. This is square root of first derivatives.
Oh, okay.
Yeah, good. All right, that's a good point. In the equation of motion, second derivatives appear. In the action in the Lagrangian, squares of first derivatives appear. Now, what's that like? That's very, very much like F equals ma and its relationship to kinetic energy. In the Lagrangian appears kinetic energy, velocities squared. In the equation of motion appears acceleration, which is q double dot. Okay. How did that happen? Well, remember what you're supposed to do. You're supposed to take the derivative of the Lagrangian with respect to q dot. That gives you some q dot, and then differentiate it again to get q double dot. That's in the equation of motion. So in the equation of motion, the wave equation, we had second derivative of phi with respect to t squared minus second derivative of phi with respect to x squared equals 0. That was equation of motion. But in the Lagrangian itself, you don't have second derivatives, you have squares of first derivatives, which is like the kinetic energy of a particle. Okay. So the Lagrangian, as a rule, has first derivatives squared. The equation of motion that follows from it has second derivatives. That's a good question. Thank you. Yes, sir.
We start out this model with the kinetic energy equal to 1/2 mv squared, which is not the relativistic energy.
No. We're not doing relativity at the moment. This is just a, we're doing...
But you end up with something and you start making relativistic conclusions at the end.
Well, not really. Not really. We just have, this has nothing to do with the speed of light. It has nothing to do with special relativity. It's just a wave moving up and down the x-axis. Now, I point out to you that if we substituted the speed of light and set the speed of light equal to 1, we're starting to see a pattern. Right? But remember, that pattern is going to be about fields, not about the motion of particles. So while it's true the kinetic energy of a particle in relativity does not have the form of 1/2 mv squared, the kinetic energy of a field does have the form of the square of not a velocity in space, but a velocity in field space. In other words, in our model, the phi direction was we were really imagining that it was a spatial direction. But now abstract from that. Just drop the whole framework that we started with, where phi was actually a motion along a certain axis, and now just think about it as a field in space. Now, there's nothing that anybody says that would tell us that a field cannot have a kinetic energy which is the square of its time derivative. It's not the motion of a particle in space, it's the motion of a field in field space. Yeah. Okay. Looks like we're going to go home a little bit early, but if there are no questions, I'm happy to stay around for a few more minutes for questions. But
You need to integrate over time also?
the action integrates, you integrate over time.
But you need another integral, don't you, for the Lagrangian?
One for the x and one for y.
He just wants you to use a double integral. Double integral sign.
Oh. All right, now convention. The fact that there's two integrals is indicated fully by the fact that there's a dx and a dt there, and there's no need to specify that one. Right, so standard convention is an integral means an integral over any number of dimensions, and it's this thing which tells you how many dimensions are there.
Well, it's really a path integral, right?
No, it's not a path integral.
The action?
It's a volume in
It's
space.
a volume integral. It's a space-time volume integral. It's not an integral along a path in space.
Well, the action would be.
No, it isn't.
Oh, not this action.
No. The action of a particle would be a path integral. Not a path integral in the sense of Feynman, but an integral along a line integral. Yeah.
If you had infinite distance between your bridge and peg, then you essentially have one set of, one fixed curve going this way at velocity c on your diagram, space-time diagram, and then one going the other way.
Well, we haven't discussed the nature of the solutions of this equation yet. Let's come to that next time. But if you didn't have a peg and a b, whatever b is, I forget, then we would just take these out to infinity, and there would be no restriction on the integral. Okay, that was good. I enjoyed that. Thank you.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.